Okay. So thank you everybody for coming today. It's a great pleasure to introduce Anton Izosimov. Anton, I just want to thank you again for agreeing to give the talk on short notice. We really appreciate that. And it's great to see a lot of new faces in the seminar. Without further ado, here's Anton, who's going to be talking about groupoids in fluids.
Thank you, and the pleasure is definitely mine, and thank you for inviting me. So I will indeed talk about, well, a certain geometric perspective on fluid dynamics that's related to the notion of a groupoid, and this is based on joint work with Boris Kessin, who I think is here or was here, I don't know. And this is, well, a part of this is work that's already done and published, and a part of it is an ongoing project. And I'll try to explain the general perspective, but I'll mostly talk about a specific example that's related to vortex sheets motion. But actually, this picture seems to be much more general, and I will mention those generalizations, or, well, possible generalizations at the end of the talk. But I'd like to start with a more classical material. So before talking about the role of groupoids in fluid dynamics, I'd like to talk about groups, which is definitely a more classical and basic notion. And so groups in fluids, and this group theoretical perspective on fluids, it goes back to Arnold to 1960s, and specifically it applies to the incompressible Euler equation. So, and this incompressible Euler equation, in most of my talk, I will be discussing specifically the incompressible Euler equation, but in slightly different settings. I'll start with the most classical one. So you have a fluid that's incompressible. Therefore, it's described by its velocity field, which we'll denote by V. And this V, because the fluid is incompressible, that means that it's a divergence-free vector field. That's just the same as saying incompressible. And well, the setting may be different. If you're a geometer, then you may think about fluid filling a Riemannian manifold. If you're an analyst, then maybe it's a domain in the Euclidean space. That doesn't matter. So this V is defined on a Riemannian manifold, possibly with boundary or a closed Riemannian manifold, or this Riemannian manifold may be a domain in the Euclidean space of some dimension n. So all of this can be considered, and well, these settings are very close to each other, basically described by the same equation. And the main hero is the Euler equation, which describes the time evolution of this vector field, and the equation looks as follows. So this V, well, it's a vector field in the domain or in a manifold, and it additionally depends on time. And if you compute the time derivative of this vector field, and to that you add the derivative of V with respect to itself. And if you're a manifold, then this thing here is the covariant derivative of V with respect to itself. If you are in Rn, that's just the usual component-wise derivative of V in the direction of itself. And the equation says that this should be a gradient vector field. So this should be equal to a gradient of a certain function. And that function, it has a physical meaning of pressure. So this is the incompressible Euler equation. And should probably say right away that this looks like a as if it's an equation on two things, which is V and P, but that's not quite the case because P can be just completely eliminated from the equation. Namely, notice that if we take the divergence of both sides here, then this term will just disappear because V is divergence free. And here we'll get the Laplacian of P. So basically you get a kind of Poisson equation that the Laplacian of the pressure is equal to something. And you also have some boundary conditions. And using that boundary conditions, you just find P as a solution to that equation. So basically this is an equation on the velocity field, and P can be expressed in terms of the velocity field. Okay, so this is the Euler equation, and well, then, what Arnold suggested was a slightly different and more geometric perspective on that equation. Namely, well, the first observation is that, well, the motion of a fluid can be thought of as trajectories in a certain infinite dimensional manifold. Namely, well, if we want to describe fluid motion, we can, in some sense, label all particles of the fluid, and then as the fluid moves, the particles move around, and then we can describe the new position by specifying the map that's taking the old positions of particles to new positions. And this one, it should be fixed once and for all, so this is a kind of a reference position. And of course, if the fluid flow is given by a smooth vector field, you integrate it, then what you get is not just a map, but it's a diffeomorphism. So this map here, in the setting of smooth solutions of the Euler equation, it's a diffeomorphism. And therefore, well, upon fixing the reference position, one can identify the configuration space of the fluid with the group of diffeomorphisms of the domain. And let's denote the domain by M. So as I said, that can be a manifold or a domain in the Euclidean space. And then, yeah, that's not exactly right what I said, by the way, because of course we cannot get all diffeomorphisms because we are looking at incompressible fluids. So this should moreover be a diffeomorphism that preserves the volume on the manifold. So if we denote the volume element by mu, then what we get is this group preserving the volume element. So this is volume preserving diffeomorphisms of M. And well, this is the configuration space of the fluid. And so any motion of the fluid can be described as a trajectory in this space. And well, there are no external forces acting on the fluid. The fluid is just moving around the manifold with the only constraint is that it's incompressible. The constraint is already encoded in the configuration space here. So basically, classical mechanics tells us that, well, the motion should be encoded by geodesics on the configuration space. That's what is known as the least action principle in classical mechanics, that any mechanical system, if you have no external forces, then it should move along basically shortest lines in the configuration space, the shortest curves or geodesics. Of course, the least action principle does not directly apply in this infinite dimensional setting. Well, I mean, at least it's not a theorem. In classical mechanics, that's something that can be proved to be equivalent to basic principles. So it's a rigorous statement. In the infinite dimensional setting, that's something that needs to be verified on a case-by-case basis. But what Arnold was able to prove is that indeed the Euler equation that we just discussed, so this equation can actually be reformulated or is in some sense exactly the same as a geodesic equation on the group of volume preserving diffeomorphisms. So that means that basically, well, at least locally, the way the fluid moves, it moves along shortest possible path. But this path, they're not on the manifold itself, but they're in this infinite dimensional group of volume preserving diffeomorphisms. And of course, well, when we talk about geodesics, we should specify the distance function or the metric on this group. And this metric, it's specified by two requirements. Well, first of all, the metric on the group, it's what's called right invariant, which means that your distance function is invariant under the right action of the group on itself. And if you think about it, it's obvious that the metric should satisfy this condition. So basically what this means is, well, the metric is coming from the kinetic energy of the fluid. And when you're computing the kinetic energy, the only thing that matters is the velocity of the fluid at every point. What doesn't matter is the particular positions of particles. To compute the kinetic energy, you don't care which particular particle is sitting at this point. You only need to know the velocities. And that exactly corresponds to the right invariance of this metric. And because it's right invariant, it's basically sufficient to specify. So this is our group of volume preserving diffeomorphisms. And in this group, we have a specific point that's the identity. And because of the right invariant nature of this metric, you can basically move things around this infinite dimensional manifold. And it's sufficient to specify this metric at the tangent space at the identity. And then, well, what this tangent space is, it's just infinitesimal diffeomorphisms. And infinitesimal diffeomorphisms, they are precisely vector fields. And in this case, because it's volume preserving diffeomorphisms, then as the tangent space to the identity, we have the space of divergence free vector fields. So this space is sitting at the identity, and then it's sufficient to specify the metric as basically a quadratic form on this space of vector fields, and then it can be moved to any point in this group. And this quadratic form is just the L2 norm of a vector field. So it's given by L2 norm of a vector field, which basically is the kinetic energy of the vector field, or twice the kinetic energy, if you like. At each point, you compute the norm of the vector, and then you integrate over the whole manifold with respect to the volume that's volume element that's given on the manifold. So that's the metric. And then Arnold proved that if you take this specific metric, you compute the geodesic equation, then, well, what you get is precisely the Euler equation. There's one, well, to be a little bit more precise, it cannot be exactly the Euler equation, simply because this description on the group, this is what's called the material description. Namely, we trace positions of all particles. So we have more information than just a vector field. So the Euler equation, on the other hand, it's not the material description, but it's just the evolution of the velocity field at every point. So these are two different descriptions. But if you kind of take this equation that describes positions of particles and rewrite that in terms of velocities, then this gives you precisely the Euler equation. Well, a slightly more geometric point of view on this is, well, what we just said is that what we look at geodesics on this infinite dimensional group, and geodesics are described by a certain second order differential equation, and a second order differential equation is first order if you rewrite it in terms of velocities, or in other words, this geodesic flow, it can be viewed as a flow on the tangent bundle to that group. So that just means that you rewrite it in terms of velocities. And the group is acting on itself by right translations. So it's also acting on the tangent bundle by right translations. And because the metric is right invariant, that means that the flow we get here is also invariant with respect to this right action on the group. And basically what you need to do, you need to reduce by this symmetry. You mod out this symmetry. And well, the tangent bundle is just tangent vectors sitting at all points. And using right translations, we can translate everything to the identity. So this quotient here is precisely the divergence-free vector fields. And by, well, reducing the dynamics by the right group action, we get to vector fields, and then the reduced flow is exactly the Euler equation. So that's basically Arnold's point of view on fluids, which turned out to be very fruitful and well, has many different applications, and also applies to many different situations, not just to incompressible fluids, but also applies in some compressible settings, in for magnetic fluids, and so on and so forth. So basically, in all these situations, what we get is geodesics on a certain infinite dimensional group, and the metric has this left or right invariance properties, and this corresponds to a certain equation in fluid dynamics. The one problem, so what we discussed for now, is that we can look at geodesic flow on the group of volume preserving diffeomorphisms on the manifold, and this corresponds to the Euler equation, or more precisely, because we're considering diffeomorphisms, this corresponds to smooth solutions of the Euler equation. And well, one situation when, well, there are on the other hand some settings where this group approach just cannot work. And well, in some sense, well, here it works because of the presence of the group symmetry. So the fluid, when we're considering smooth fluid flows, it has this group symmetry, and because of that, everything can be rewritten in terms of the group. There are some situations, though, where that symmetry is lost, and I'll give an example of that situation, and that will actually be our main example for today. So we'll look at the so-called vortex sheet flows. So basically, we are still looking at the same Euler equation, but now we'll consider certain solutions of that equation that will no longer be smooth, but they will have discontinuities of a certain kind.
Could I ask just one? If you consider Udovich solutions, so bounded vorticity, is there a geometric picture?
I don't think so. So I think you need, well, I mean, you certainly don't need infinite smoothness, but you do need a certain amount of smoothness for the group picture to make sense. And well, now I will describe a particular class, well, of solutions that are still quite nice, but they are not everywhere smooth. And already in that setting, we need to extend groups and consider groupoids instead of groups. So I think in general, applying groups for very singular solutions is problematic.
Yeah, I guess in the Udovich case, you don't have diffeos, right? I mean, because you lose regularity on the flow, but you have homeomorphism. I mean,
yeah.
Yeah.
And well, again, up to certain level of regularity, this, well, diffeomorphisms of finite smoothness, it's still a nice group. But if the regularity is too low, then it becomes a weird object that's not behaved in a nice way.
Yeah, I think uniformly in time, all you have is continuous for the flow for Udovich.
Yes, and that's probably I mean the group of homeomorphisms is, I mean, you can still consider it, but that's not a manifold of any kind, and it will not have any nice differential geometric properties. I don't think you'll be able to define geodesics, so you need a certain level of smoothness. So the returning to a vortex sheet flows, this is the following type of flows. So let's assume that in our manifold there is a fluid flow, and now instead of being continuous and smooth, the fluid there is a hypersurface inside this M, and we'll denote that by gamma. And what happens is that the fluid flow breaks along that hypersurface. So it's continuous and smooth outside of the hypersurface, but on the hypersurface itself, it's allowed to have a discontinuity. And well, specifically, since we still want to consider the incompressible case, not any kind of discontinuity can be allowed. So you don't want this. So you don't want fluid to be moving in two opposite directions on two sides of this hypersurface, because, well, that would violate the incompressibility constraint. But what you actually want is that if you have, if you approach the surface on one side of the discontinuity surface, and on the other side, well, you allow discontinuity, but the normal components of the vector fields on two different sides, they should agree. So this is basically what replaces the, so say here we have a green fluid, and at this point it's moving here, and on the other side we have blue fluid. Then it can be moving differently at this point, but with the same, the normal component should be the same. If you subtract the two velocity vectors, that should be tangent to the discontinuity surface. So basically one layer is allowed to slip along the other layer, but in the normal direction, they should be moving in the same way. So, and away from the surface, the constraints are just as before. And this surface is what is known as a vortex sheet. And well, there are, this is, as I said, this is an example of a setting where the groups are no longer applicable. And it's quite easy to see why that should be the case. Well, first of all, of course, here the fluid flow is not going to be given by diffeomorphisms. That's obvious because your vector field is discontinuous. When you integrate, you don't get diffeomorphisms. So if it's a group, then it must be a different group, not, at least not diffeomorphisms. But actually, it's quite easy to see what kind of object that is. So if you integrate this type of a vector field and it's time dependent, you integrate it, then well, the motion of particles is given by a map that is a diffeomorphism on kind of one half of the manifold, and it's also a diffeomorphism on the other half. But there is this discontinuity surface, and it doesn't have to be mapped to itself. It's generally mapped to some other surface. It moves because, well, basically the normal component of the vector field moves the surface. So you get this type of diffeomorphism that's in some sense discontinuous across a hypersurface. And well, one thing that's clear is that, well, diffeomorphisms like that, they do not form a group. They're not closed under composition. Well, if you have one diffeomorphism that's discontinuous along this surface here, and you try to compose it with another one that's discontinuous along some other arbitrary surface, then the composition is just going to be a complete mess, because basically, well, this discontinuities, they add up together, and it's basically going to be discontinuous along a union of two surfaces, which may intersect in a very complicated way. So, which means that we need to extend the class and it doesn't. Again, it doesn't seem possible to find any group type object that contains all this diffeomorphisms. So what we should consider here is not a group, but some other type of structure. And another indication of that is actually, it can be seen on the infinitesimal level. If we return to this picture here, then, well, we're looking at the group of volume preserving diffeomorphisms, and the actual Euler equation is in the tangent space to that equation. And because, so this thing here, the volume preserving diffeomorphisms, it can be viewed as an infinite dimensional Lie group. It's a group. It's also a Frichet manifold, so it is a Lie group in a certain sense. And because of that, this tangent space is the identity. It's a Lie algebra, should have a Lie bracket type of structure. And in this case, this structure is very well known. It's just the commutator of vector fields. And the fact that volume preserving diffeomorphisms form a group on the infinitesimal level translates to the fact that the Lie bracket of two divergence-free vector fields is again a divergence-free vector field. That's just an infinitesimal expression of this thing being closed under composition. But now if we look at this vortex sheets case, we immediately run into a problem. Namely, well, here we should consider vector fields of this specific kind. So they are divergence-free in both parts of the manifold. They're possibly discontinuous across a hypersurface. And moreover, the normal components agree. But it's easy to check that this condition that the normal components agree is just not closed under the Lie bracket of vector fields. So of course, when you compute the Lie bracket, it will still be divergence-free here and here. This is fine because that condition is preserved, but the condition on the normal component will break down. So this is the infinitesimal reflection of the fact that there is no group structure here. Well, unless we want to extend the class of vector fields, but if we just want to describe this setting and this, okay, and so this was one of the motivations for this work on vortex sheets that we did. So we still wanted to get some kind of geodesic description, but we observed that the group setting seems to be not applicable here. And another motivation was a work by Christian Loschke, which was his PhD thesis he wrote under Felix Otto a few years ago, which, so as I just said, well, this group geodesic approach doesn't apply to vortex sheets. But what Loschke shows is that actually for specific kinds of vortex sheet flows, one still has a certain kind of a geodesic description, but it's actually a different one. So namely, he considers a specific class of vortex sheet motions. So these motions are of the following kind. So here, again, we have our manifold separated into two parts, and in each of them we have a divergence-free vector field. But moreover, it's not just a divergence-free vector field, but it's at the same time a gradient vector field, which means that it's a gradient of a harmonic function because you want the gradient to be divergence-free. So there are two harmonic functions sitting in two parts of the manifold. You take their gradients. Of course, there are no global harmonic functions, but here we kind of have a harmonic function that has a singularity along this surface. So we are fine. We can consider functions like that. And Loschke considers vortex sheet motions that are of this kind. So if you think this can be also interpreted in terms of vorticity of the vector field, because here we have a gradient vector field and it has zero curl. It has zero vorticity, but that's outside the hypersurface. But because we have this discontinuity hypersurface, the vorticity actually becomes infinite at the hypersurface. So it's not zero vorticity globally, which is, well, which would be impossible for, well, not exactly impossible, but you cannot have a global harmonic function. So if you are, say, on a sphere, you cannot have a solution of the Euler equation with zero vorticity. But here, the vorticity actually behaves like a delta function that's concentrated on this hypersurface. So that's an alternative description of this special solutions to the Euler equation that what were considered by Loschke is that the vorticity is a delta function attached to a hypersurface. And what he does is he shows that this actually admits a geodesic description, but it's no longer a geodesic description on the space of diffeomorphisms, but it's actually a geodesic description on the space of hypersurfaces. Namely, well, here we have this discontinuity hypersurface that we call a vortex sheet. And well, this hypersurface, it evolves with the flow, and one can consider the space of all possible hypersurfaces. Well, perhaps you'd want to consider all hypersurfaces of a given diffeomorphism class, but that doesn't really matter. So we can look at this space of all possible vortex sheets, and then Loschke proves that, vortex sheet solutions of this type with zero vorticity outside, they can actually be described as geodesics on that very space of vortex sheets, on the space of hypersurfaces. So here, instead of diffeomorphisms, we consider the space of hypersurfaces. And well, this may sound a little bit strange at first because it seems that, well, it cannot be described by geodesics on that space because it's not an evolution on that space, because we have more information here. We have a hypersurface, but in additionally, we have these two vector fields. But actually, well, because these are gradients of harmonic functions, they are uniquely determined by the normal component at the boundary, just by uniqueness of the solution to the Neumann problem. And if you have a vector field at the hypersurface that's normal to this hypersurface, then you can think of this as an infinitesimal deformation of that hypersurface. So actually, the space of vector fields like that, it's just a space of hypersurfaces and this normal vector fields attached to a hypersurface, but that's precisely the tangent bundle to the space of hypersurfaces. So actually, the space of this vortex sheet type fields with zero vorticity outside can be identified with a tangent bundle of the space of hypersurfaces. And then, well, the Euler equation restricted to this type of solutions gives you a flow on the tangent bundle. And Loschke shows that this flow is exactly a geodesic flow on a certain metric, which kind of agrees with the fact that the geodesic flow is an equation on the tangent bundle. And one should say that the metric in this situation is quite complicated. In particular, it is of non-local nature. So to define a metric, you should pick a normal vector field like that and then say, well, what the value of the metric on that vector field is. And the construction is that you consider all possible extensions of this vector field to globally define divergence-free vector fields. You compute L2 norms for all of them, and then you minimize overall possible extensions. So that's the metric. And in particular, it's a non-local metric because, well, to compute it, you need to know things on the whole manifold, not just on the hypersurface. And if you write it explicitly, well, it's not a differential expression in terms of the vector field, but you actually need to integrate things as opposed to differentiating things. So, and then taking geodesics for this kind of metric, Loschke shows that this corresponds to vortex sheet solutions of the Euler equation. And of course, by vortex sheet solutions of the Euler equation, I mean weak solutions, because there is a discontinuity, so you cannot, it cannot satisfy equation in the, well, in a straightforward way, but one can still make sense of what it means for a discontinuous object like this to satisfy the equation. That's called a weak solution. And Loschke shows that weak solutions of this particular kind, they have this geodesic description on the space of hypersurfaces.
So this, I mean, the equation that governs vortex sheet motion, as far as I understand, there's a well-posedness theory locally for the Cauchy problem, well-posedness theory locally in time in analytic spaces, and then it's ill-posed outside of analytic, right?
So, well, as far as that, it's ill-posed in the sense of Adamar. So there is a problem with continuous dependence on the initial conditions. Yeah.
Mhm.
So
In principle, maybe there's, I don't think it's ever been shown, but maybe there's multiplicity of solutions. Even, I mean, I think it's conjecturally believed that, you know, even a flat vortex sheet could initially be initially flat, that's stationary, but then maybe there are multiple solutions emanating from that. And I wonder if, yeah.
I mean, yeah, sorry, go ahead.
No, you say.
Well, that would just mean that there are multiple solutions for this geodesic equation too. So this, I mean, this is a in a sense that's an identification between two flows. So it's not saying any and between their solutions, but I mean, because it's an infinite dimensional Riemannian manifold, no, it's not guaranteed that the geodesic problem is well posed. Well, I mean, for instance, for the classical Euler equation, the geodesic formulation is actually helpful for proving well, kind of well-posedness and uniqueness and existence result, because in that setting, well, it can be shown that the geodesic problem it behaves nicely, but in this setting, well, it's not known essentially. So, and yes, this is known to be a kind of not very well behaved problem. Yes.
I mean, I guess just one thing that could be interesting is that, you know, once you formulate things via this type of action principle, then you can ask different questions. You don't have to talk about the Cauchy problem. You could talk about the 2-point problem. So, you know, given two configurations, can you connect them? And the questions like that may not be opposed in, you know, in classes of surfaces that aren't analytic. I don't know. Maybe that's not ill-posed because, but for the Cauchy problem, I guess analyticity is somehow crucial here. I just wonder if it shows up at all in your description.
I mean, we don't assume analyticity. We could, I guess, and but I mean, it works in any sufficiently smooth setting. So one can do either C infinity or one can do Sobolev spaces for the description. It doesn't really matter. But of course, well, if one asks questions like whether there is a solution to the 2-point problem, well, yeah, then it probably depends. And I think that for this particular problem, there are basically no results on this. But this Loschke metric, it's very complicated. It's non-local, so I would assume it should be pretty hard. And in some sense, so now I will talk about the approach that encapsulates both this Loschke metric and the one that was in Arnold's description. And that in some sense, it sort of, well, yeah, that probably is not quite right. Well, but in some sense, it localizes it. So maybe it's actually one can say something from that other point of view I will describe.
Thanks. Yeah.
So basically, when we started working on this vortex sheet problem, so we had this two descriptions with no apparent connection between each other. So we have the setting of smooth flows due to Arnold, and in that setting we have geodesics on the diffeomorphism group, and we have this vortex sheets. But recall that what Lyoshki considered is not arbitrary flow with vortex sheets, but these are, well, one can say it's call it potential vortex sheets, because these are flows that are potential outside of hypersurfaces. And for potential vortex sheets, the description is in terms of geodesics on the space of hypersurfaces. And well, basically what we wanted to do, we wanted on one hand to generalize, well, this and this to the setting where one can consider flows that have a vortex sheet but are just smooth outside of the vortex sheet, not necessarily potential. And well, hopefully that generalization should kind of give both descriptions. In particular, should connect them together. And we actually managed to do so. And it turns out that, well, in order to do that, one needs to extend this group point of view of Arnold and consider objects that are called groupoids. So basically, let me say just a couple of words of what a groupoid is. So a groupoid is basically a group with only partially defined composition. So the simplest way to imagine a groupoid, so assume that you have a set, and then you consider self-maps of that set of a certain kind, and well, typically this form a group. So you can consider, I don't know, any self-maps, continuous self-maps, any kind of self-maps like that, they form a group. So you can invert things and you can compose things. Now, instead of self-maps, you can consider maps between different objects, and you don't want to consider all maps, but you only consider bijective maps. Or maybe, well, maps in some other category like homeomorphisms. And then you can still invert things and you still have identity maps there, self-maps. But in general, you cannot compose. So for instance, this map cannot be composed with this map, and two maps can be composed only under a certain condition. Well, namely, well, clearly the domain of one map should coincide with the codomain of the other. And the groupoid is basically the abstraction of this picture. So a groupoid is, again, it's, well, some kind of a set, but on this set, you have a product operation, but it's not always possible to multiply things. But it is exactly possible when there is a condition like this. And the abstract version of this condition is that you have another set, which you call the base of the groupoid, and you have two maps from G to the base, and they're called source and target. And think of B as this collection of objects here, and source is the domain, target is the codomain. And then you can only compose when the, well, source of one coincides with target of the other. So G1, G2 is defined whenever target of G2 is equal to the source of G1. So this is what the groupoid is, and there is a bunch of axioms, but they're all group-like axioms. So you have, it's associative. You can invert things. There are identity elements, but here it's more than one identity element, because each of these sets there is an identity map of this set to itself. But basically, it's like a group, but with this additional source and target maps that control composition that tell you when composition can be taken and when it cannot be taken. And now, well, one can notice that this discontinuous diffeomorphisms we were looking at, they have precisely this type of structure. So we have a diffeomorphism from here to here and from here to here. And well, I can actually compose this with another discontinuous diffeomorphism, provided that that other one is discontinuous across, well, this resulting hypersurface, right? If I have something like this, then I can take the composition of these two maps and it's going to be well defined and it's going to be a map of the same kind. So basically, for each map, I have two hypersurfaces, the starting hypersurface, which is this one, and its image, so the resulting hypersurface. And I want the resulting hypersurface of the map I apply first to coincide with the starting hypersurface of the map I apply second. So, and that's precisely that groupoid structure with source and target maps. And here the base of the groupoid is played, the role of the base is played by the space of hypersurfaces. So here we have, so we consider this discontinuous diffeomorphisms, and by discontinuous I mean discontinuous across a hypersurface. And well, these discontinuous diffeomorphisms, they have this groupoid structure, and it's the base of that groupoid is the space of hypersurfaces. And then, well, this discontinuous diffeomorphisms, they form a groupoid like that, and we indeed showed that, well, this can be considered as a Lie groupoid in the category of Fréchet manifolds. And when one takes this point of view, things kind of start to make sense. So first of all, recall that, well, one problem that we had is that, well, discontinuous diffeomorphisms in general cannot be composed. But now, well, this groupoid point of view, well, it definitely resolves this problem because it tells us when exactly we should be able to compose diffeomorphisms like that. And well, if that condition is satisfied, then yeah, we can compose and the result is a map of the same kind. And another problem was at the infinitesimal level. Namely, well, the infinitesimal object corresponding to our discontinuous diffeomorphisms is this discontinuous vector fields, and we notice that they do not form a Lie algebra because the Lie bracket doesn't preserve the continuity of the normal component condition. And again, the groupoid point of view explains why that should be the case, because, well, for a Lie group, the attached infinitesimal object is the Lie algebra, where you have bracket of vector fields. And for a Lie groupoid, that's no longer the case. In that case, well, the corresponding object is what's called a Lie algebroid. It's a more complicated structure. And, well, basically in this setting, what it means is that if you take just a Lie bracket of two discontinuous vector fields, well, it's no longer in the space. This condition of continuity of the normal components fails to be satisfied, but one should add certain correction terms to the bracket of vector fields. And when you add this correction terms, then, well, the bracket has the right form. And this correction terms, they correspond exactly to this algebroid structure that one should expect for, well, that's coming from the groupoid structure. And then well, the first main result we prove in our paper on vortex sheets with Boris Kessin is that Arnold description generalizes to this setting. So what we prove is that, well, first of all, one can construct a similar metric similar to the one considered by Arnold, but on discontinuous diffeomorphisms instead of the usual ones. And now it's a right invariant metric on the groupoid, and one can look at the geodesics of that metric. Again, well, we don't know if the initial value problem for them is generally well posed. Apparently not. It shouldn't be. But well, all this identification results, they should be interpreted like this. Whenever the corresponding geodesic is well defined, then this gives you a solution to the equation, and the other way around. If you have a certain solution, that gives you a geodesic. Maybe you cannot find a solution for, or maybe there are many solutions for some initial conditions. This means that there will be several geodesics going in the same direction from the same point. And the theorem that we prove is that geodesics of an L2 type metric on a groupoid of discontinuous diffeomorphisms, they correspond precisely to vortex sheet type solutions of the Euler equation. And again, of course, one should consider weak solutions, because vortex sheet vector fields with vortex sheets are discontinuous. So this corresponds to weak solutions of Euler equation of vortex sheet type. But actually, well, the weak formulation of the Euler equation for this particular solutions, it can be regarded like this. So you have these two parts of the manifold. So in each of them, the vector field satisfies the usual Euler equation. And then there is a certain condition on the pressure functions that they should, well, the pressure, there is one pressure function in one part, in the other part, but actually on the interface, the pressure function should stay continuous. So that's equivalent to the weak formulation of the Euler equation for this particular type of the vector fields. And we prove that this corresponds precisely to the geodesics on this groupoid. And one thing that I already mentioned, that, well, now instead of this non-local metric in the Loschke description, here we actually have a metric that's local. It's an L2 metric, so therefore it can be viewed as a sort of localization of the Loschke description. And well, so, and of course, well, this theorem, it can be viewed as a generalization of Arnold's theorem, because, well, a smooth flow can be viewed as a particular type of a flow. With a vortex sheet, is just this vortex sheet surface is empty, and in that case, the groupoid degenerates into a group, and this gives precisely Arnold's description. And the other thing that we establish is the connection with this other description by Loschke. So we have this space of hypersurfaces, and now we have a flow that lives here. So we consider geodesics on the group of discontinuous diffeomorphisms. Loschke, on the other hand, considers geodesics here. And they correspond to some particular solutions of the general problem, namely to those fields that are potential outside of the interface. And the question is how to connect these two geodesic descriptions. And then we show that this can be done using the concept of Riemannian submersion. So a Riemannian submersion is basically a map like this. So assume you have a manifold M, and you have a manifold N, and on M you have a Riemannian metric, and there is a map between them. And this N, it's of a smaller dimension, and this map is sort of like a projection, so that the preimage of every point in N is a manifold, submanifold inside M. And then this, if you have a Riemannian metric here, then the map is called a Riemannian submersion. if the fibers of this map, they're all equidistant from each other, which means that if you pick a point here and measure the geodesic distance to a different fiber, then it doesn't depend on the point. It's the same distance for every point. So in that case, you say that it's a Riemannian submersion. Well, an obvious example would be a projection of R2 to the horizontal direction. Then the fibers have vertical lines and they're clearly all equidistant from each other with respect to the Euclidean metric. And actually, well, if you have a map like that, we started with having a metric just on M, but this also induces a metric here, because now we can declare basically that the distance between 2 points here is the distance between the corresponding fibers in M. And that's well defined because of the equidistant property. So each time we have a map with equidistant fibers, we also have an induced metric in the image of that map. So that's one property of submersions. And another property is that, well, there is a certain identification between geodesics in this space and in this space. And well, it's not valid for arbitrary geodesics. If you just take any geodesic in M, then, well, you cannot really relate it to a geodesic here, but you should consider what's called horizontal geodesics. So these are basically geodesics that are perpendicular to fibers. Like in our R2 example, that would be just horizontal lines. And then what's true is that horizontal, if your geodesic has a horizontal initial direction, it forever stays horizontal. And moreover, horizontal geodesics, they can be identified with geodesics on the base. So there is an identification between between geodesics on the base and horizontal geodesics on the total space. And now we can apply this notion of a Riemannian submersion to this picture we just described. Namely, well, we consider this discontinuous diffeomorphisms. And each discontinuous diffeomorphism, it has a source and target, and both of them are a hypersurface. And the source can be just fixed. So we can consider diffeomorphisms that are discontinuous across some fixed hypersurface. That's actually sufficient. So with fixed discontinuity hypersurface, it's only the source surface that's fixed, but the resulting surface, it may be arbitrary, and that's given by the target map. And then we have a target map that's taking this to the space of hypersurfaces. And then what we show is that this map, well, we have an L2 metric defined here. It's basically just the L2 norm of a vector field. So it's a very simple local metric. And then we show that relative to that metric, this map is a Riemannian submersion. So it has this property of fibers being equidistant from each other. And because of that, well, it must induce a metric on hypersurfaces. And then it turns out that if you apply this procedure and compute the induced metric, then the induced metric is already non-local, and it's precisely this Lyoshke's metric on hypersurfaces. So it's induced by the L2 metric by means of this Riemannian submersion. And because of the identification of geodesics, well, we see that geodesics here, which according to Lyoshke should correspond to potential vortex sheet motions, they should be identified with horizontal geodesics. And then, well, the horizontality condition, it turns out to be precisely, well, the condition of being potential outside of the interface. So that way we recover the result by Lyoshke, because we have a geodesic description here. If we restrict the horizontal geodesics, that's potential vortex sheets, and then using the submersion they're identified with geodesics on hypersurfaces. So that basically gives, well, a geodesic description for general flows with vortex sheets. And also, as a particular case, one recovers earlier results by Arnold and also by Loschke. So they're both kind of hidden in this general groupoid construction. And well, that's basically the results, our results on vortex sheets. And well, now we're also trying to extend this approach on other settings. And it's actually clear that it should be applicable in many different situations because, well, here the problem with vortex sheets was that there is no group symmetry anymore because there is this specific, the problem of smooth flows, it's in a sense homogeneous. We have the flow behaves in the same way on the whole manifold. Because of that, we have a group symmetry. And then when we have this hypersurface of discontinuity, we'll lose the group symmetry. And instead of that, it's a groupoid symmetry. And well, there are many other problems that are also inhomogeneous in the same sense. And because of that, there is no group symmetry, but one can still use groupoids. So for example, one can consider free boundary flows. So it's a fluid flow where the boundary can move with the fluid. Then again, well, it's clear that this, so the domain filled by the fluid may change with time as time goes, and then we are forced to consider diffeomorphisms between different domains. And this again no longer form a group, but it's still a groupoid. So apparently one can use the groupoid description to handle this situation. And then there are other cases when the fluid is for a certain reason inhomogeneous. So for example, there is this problem of fluid structure interaction. So you have a solid swimming in the fluid. And then again, because the solid can move inside the fluid, that means that the domain filled with the fluid will change in time. And because of that, again, you have a groupoid instead of a group. So there is also this other problem, which is in some sense a relaxation of the vortex sheet problem. So it was considered by Brenier. So the idea is that, well, basically you can think of the vortex sheet motion as that you have two different fluids. So you have one fluid here and another fluid here. And then, well, since one of the fluid occupies only one part of the manifold, if you look at the density of that fluid, it's 1 here and 0 here, which means that if you denote this domain by d plus and this by d minus, then the density of one of the fluids is the characteristic function of the domain d plus, and the density of the other fluid is the characteristic function of the domain d minus. And then, well, the sum of this is obviously 1 because the union of the domains is the whole thing. And then this problem can be relaxed by replacing these two densities by two smooth densities that add up to 1. And as I understand the motivation for Brenier, the motivation for doing that was precisely that, well, there are certain well-posedness problems with the vortex sheet equation, but then if you relax it, then supposedly it behaves better. In particular, Brenier has some results on the 2-point problem in that setting. But actually, this relaxed vortex sheet problem, it can be also regarded as just the motion of two fluids that are mixed together. And the sum of densities being 1 means that, well, when you consider this as one single fluid, then it still satisfies the incompressibility condition, but just there are particles of two different kinds. That's actually equivalent to Brenier's formulation of the relaxed vortex sheet problem. And apparently one can use groupoids to handle this situation too. Well, here it's not, of course, even obvious what the groupoid should be, and this is still very much work in progress. So, but this is another problem we're thinking about now. And I should probably stop here. And thank you.
Thanks a lot, Anton. Are there any other questions for Anton?
So these groupoids, can they be written as sort of a disjoint union of groups? And does that have an interpretation back to the groups we know from Arnold, for example?
Well, it's not exactly a disjoint union of groups. I mean, well, of course, when you consider, say, diffeomorphisms from here to here, then, well, this can be identified with a group, because if you consider two such diffeomorphisms, you divide one by another, that's a self-diffeomorphism. But it's, first of all, it's not exactly disjoint. So it's, in some sense, it's a union of groups, but it's not disjoint. And also this identification with a union of groups, it's not very natural. And because, well, the thing is that so the group corresponds to the, well, if the vortex sheet is not moving at all, that's a group situation, because the fluid is moving in this part independently and in this part independently. So that's a group situation. That's actually just a direct product of two Arnold's groups. That's it. But when the vortex sheet is moving, then in some sense you are moving perpendicular to the group direction. So I think it's might be, so locally you may think of this object as a product of the group and the space of hypersurfaces, but and you have a certain kind of motion in the group direction, which is the fluid motion, and you have motion in the hypersurface direction, which is the motion of this vortex sheet. But it's some rather complicated composition of these two motions. But I don't think that it will have a nice reformulation purely in the group setting. So does that answer?
Yeah, no, thank you. Yeah, because it seems locally like a group. You can sort of write it out as these sort of union of
right.
groups.
You could do that, but I guess the equation will not have a nice form in if you do that, because you do have this group type fibers, but then on every fiber you will have different equations. So it's no longer that Euler equation, but I guess you could view it as an Euler equation with some forcing of certain kinds, some extra terms, but I don't know if that helps.
So Anton, these results weren't sensitive to the dimension, right? This was just an arbitrary, M was just a.
Yeah, the dimension doesn't matter. Yeah. Well, finite dimensional M. Well, in the paper we consider the setting of a closed manifold. I guess it could have a boundary. This shouldn't really. I mean, well, every time you have a boundary, you should kind of keep track of the boundary conditions, but in principle, it doesn't matter much. So we consider the setting of M being, well, an arbitrary Riemannian manifold on a dimension. We did have some topological restrictions on the paper. So one thing that we required is that this vortex sheet, it separates M into two parts, which in principle, it doesn't have to be so. So if you have complicated topology, so let's say you have an annulus shaped domain, then the vortex sheet, or maybe a better example is that it's a torus. And then the vortex sheet may be just kind of one circle on this torus, and then it doesn't separate the torus. So we didn't discuss this case. So we do have certain topological restrictions that need to be satisfied for the description to be valid. But again, we just didn't want to deal with topological issues. I don't think it would be hard to generalize to that case, but the dimension doesn't matter. Of course, the analytic behavior may be completely different in different dimensions, but from this geometric perspective, it's really all the same. Well, it's same for Arnold's picture. It works in the same way in all dimensions. Well, if you look at finer features of the equation, like for instance, from Arnold's description, you can derive this standard conservation laws, and derive many conservation laws for the Euler equation in 2D, and then also in all even dimensions, but it's not true for odd dimensions. So here, well, similar things show up, but in principle, for most of this, the dimension doesn't matter.
I see. Just to follow up on that, since it can be reformulated in any dimension, of course, one of the open problems for the 3D Euler equations is finite time blowup. So this is just a general question about the Arnold formulation, but how would such a result manifest in that formulation? Like a finite time singularity of.
Just in the same way, I'd say you would have a singularity for the geodesic flow. Well, I mean, it's okay. It's not exactly true. Well, that depends on what kind of singularity you have, right? Because your vector field is in some sense the derivative of the flow, right? So it may be the case that the flow could still be non-singular, but then you would have some singularities at the derivative level. But I don't think that that's something that's possible for the Euler equation. That's something that happens for. So there is this version of the Euler equation that's called the Burger's equation, and it's basically the Euler equation where you remove the incompressibility constraint. So you don't have this term anymore. You just have this, and then it's a geodesic flow on just the diffeomorphism group. And for that equation, it's well known that there are singularities, and it's quite easy to see that, especially if you look at the one-dimensional case already. In that case, you have this kind of well, what is it called? Like breaking waves. So the solutions, they essentially become multivalued in finite time. And then, well, in that case, in some sense, at the level of geodesics, things are still, well, it's not exactly true, but you can still make sense of the flow beyond the blow up point at the geodesic level. But at the level of the equation, things go bad. But for the Euler, I would think that blow up at both levels should be more or less equivalent.
So what does it say past the blow up for example, in the Burger's case?
So in the Burger's case, well, basically the Burger's case is the Burger's case. What it describes is so in the one-dimensional case, for example, you have a particle sitting at every point in the line. And then each of these particles is moving with its own velocity. So that's what the Burger's equation describes. And then, well, clearly at some point, well, faster particles start overtaking slower particles. And then, well, this corresponds to, well, to a blow up, essentially.
Yeah.
But at the level of particles, there is no blow up, right? The particles are still moving fine. It's just a question of because the way this is described in the Euler equation is that the Burger's equation, it tells you the velocity of the particle at a position x. So that's the v of x function. And then, well, as particles start overtaking each other, v of x becomes a multivariate function. But at the level of the material description, at the level of particles, well, it's no longer a diffeomorphism though, but you still have a map, because for each particle, you can say where it moved in time t.
I see. So it manifests in just losing the fact, losing, you know, losing the fact that it's a diffeomorphism.
Yeah,
Okay.
at the level of the Lagrangian description, at the level of particles, yes. At the level of the Burger's equation, well, essentially you get a multivariate solution.
Could you look at it as manifesting as like the number of path or connected components of the groupoid grows? So for the groupoid, you can consider the equivalence relation. There exists, I guess, a morphism from X to Y, and you could form that equivalence relation and look at the equivalence classes. And when there's a singularity, that sort of like those equivalence classes change. Because if everything's fine, then all the maps are sort of composable, and it's only when this emerges that the equivalence classes start to grow.
Yeah, I mean, I can imagine that being relevant, but somehow our model is only valid for the number of equivalence classes staying the same. So I mean, it's ideally, like the nice thing about this Burger's equation is that this model with particles, it allows us to model situations beyond the blow up point. And because of that, so one can describe this, well, all the blow up completely for the Burger's equation. Well, at least in the one-dimensional cases, there is a lot of work on this in the multi-dimensional case, but it's more tricky. But for the Euler, well, one would want to have a kind of a similar model that's in some sense more general, and but in particular, well, here in the Burger's setting, we allow for maps that are not invertible. And so when the blow up happens, the map fails to be invertible. And there is no similar description for the Euler equation as far as I know. So this is not known whether one can. So ideally, one maybe would extend it from diffeomorphisms to smooth or non-smooth maps that are non-invertible, but are, well, something like similar to what we have here, maps of this type. But this hasn't been done.
So there's something I read in one of Schnirelmann's early papers, and I thought it was interesting, but probably you or Steve could correct me if I say it wrong. It's sort of a failure of the connection, but it's still interesting. He studied in that paper the 2-point problem, and he just made the point that in finite dimensions, if the 2-point problem fails to have a solution for some configurations, then it means that there's a geodesic that terminates in finite length. So it's geodesically incomplete. So that fails in infinite dimensions. But what Schnirelmann proved is that there are in 3 dimensions configurations that are isolated. There's no shortest path between them. Namely, any path you can find a shorter one. And if the analog of the finite dimensional result, which is like a Hopf-Rinow theorem, held in infinite dimensions in that strength, then it would be an indication of some singularity formation, because you leave the group the geodesic terminates, you leave the group. That's what singularity formation means in that context. So, but I think not, but it's nice anyway.
I don't know if Anton's frozen. The Hopf-Renoff theorem fails badly enough in infinite dimensions that, like, even that example is not really considered good evidence one way or the other as to whether Euler breaks down.
Yeah.
But yeah, I mean, there is a sort of big chunk of research in infinite dimensional geometry focused on just trying to understand these weird phenomena in other situations to try and get a sense of, you know, how close or far Hopf-Renoff is to working. And that's maybe in the back of people's minds.
So it's interesting, I guess, that in 2D it's still open, but maybe it's conjecturally true, right? There's 2 points can be connected by a shortest path in 2D. And of course, 2D is different from the point of view of existence theory. By the way, I just wanted to ask Anton, is there a steady state action principle a la Arnold also for your framework?
Yeah, I mean, well, the description of steady states in Arnold's picture, it's basically comes from the fact that, so you have this geodesic flow on the group. So one can view it as a flow on the tangent bundle, or maybe it's better to look at the cotangent bundle, because that puts it in the Hamiltonian setting, and it's a Hamiltonian system on this cotangent bundle, and you perform reduction with respect to the group action, and then you get into the dual of the Lie algebra, and in the dual of the Lie algebra, you now have a Hamiltonian formulation on coadjoint orbits. So the group acts on the dual of the Lie algebra, and the steady states, they correspond to critical points of the energy on coadjoint orbits. But that basically just follows from the group description. So we have a similar situation, but now instead of the dual of the Lie algebra, so now you have an object that's, so a Lie algebra is a vector space with a structure, and in the groupoid setting, you get an algebroid that's not going to be a vector space, but that's going to be a vector bundle over the base, over the space of hypersurfaces. And that has a structure that replaces the Lie bracket. And then you take the dual bundle, and that's, so in that dual bundle, there is a Poisson structure. So there is an analog of coadjoint orbits. And then steady states, they do again correspond to critical points of the energy on those orbits. Yes.
I wonder if there's so a result like Vishik's result in 3D, just that the second variation is sign indefinite on any stationary configuration. Namely, I kind of expect that any vortex sheet configuration would be unstable.
Well, at the moment we don't have any results on this, but I would imagine this vortex sheets to be unstable in any reasonable sense. So you can look either at that, or could look at curvatures. So at the group level, because then the negative curvature is also an indication of instability, and because this vortex sheets, they're known to be ill-posed. I would imagine that's an indication of scalar curvature being unbounded from below. So it's you consider different two-dimensional directions, then it can be as basically as small or as large negative as you want. But again, that's not something that has been proved, but well, intuitively that's something that has to do with ill-posedness, because that, well, this magnitude of the curvature is how fast your geodesics diverge, and then this means that you can vary the direction and you can get geodesics that diverge arbitrarily fast from the given one, which would probably correspond to the discontinuity, discontinuous dependence on the initial condition. But in the group setting, this curvatures are known to be bounded from below, as far as I know. Is that right, Steve?
Bounded below in. Wait, so for what, 2D Euler?
Or 3D Euler. So if you look at sectional curvatures at a given at a point, then those are. But you consider sectional curvature as a function of the direction, and I think that's bounded below.
So if you fix one velocity field, right,
Yeah.
and then you consider it as a function of another velocity field you plug in, right? The only bound I've ever seen or ever been able to make work is basically C1 on the given velocity field, and then you have an L2 bound on what's left. So yeah, like if you have an absolute C1 bound on your velocity field, then yes, absolutely, it's bounded below. But I think that's the tricky part, right?
Yeah.
Getting C1 bound.
Yeah, right. Of course. I mean, this.
So I mean, you know, if we had something like, you know, a universal lower bound that didn't depend on that C1 norm, then I think you'd get global existence for free for a 3D Euler. But that's a complication.
Yep, I see.
Well, it is 8 o'clock now. We usually end the seminar at this time. Are there any other questions for Anton? All right, well, Anton, thanks a lot for the wonderful talk.
Yeah, thank you.
Thank you.
Thanks.
And
Thank you.
And would you send me a link to the recording?
Yeah, absolutely. When I get the link, I'll send it to you.
Thank you.
Yeah, no problem. And regarding next week, everybody, there's currently no speaker lined up, but there will be a few in October. So we'll keep you posted. Okay. Thanks very much, everybody. Anton, thanks again, and have a good night, everybody.